of mine in electrical and computer engineering, and he's going to tell us a little bit more about nanophotonics.
That's right. So I'm going to talk today a little bit more about nanophotonics, and in some ways, maybe this talk should have come first, since it's probably a little bit more fundamental than some of the other talks you've seen. But in other ways, maybe this is well placed, because I think in this talk, what I want to try to do is wrap up some of the things that you've already heard. You've had a lecture from Professor Choquette on nanophotonics. You've heard from Professor Liu about plasmonics and metamaterials. And today I'm going to try to, and you've also probably heard, I think Professor Bhargava has already spoken on IR spectroscopy. So today I want to try and combine all of that, and what I want to talk about is how we can do nanoscale photonics with micron-scale light, and why we might be interested in that, and what sort of things we might be able to get out of that. And I've tried to put a sort of bio-y spin on this. Obviously, my background is more sort of from the physics and electrical engineering side of things, photonics side of things, but I've tried to sort of place this in the context of biophotonics to the best of my ability. Okay, so what I want to start talking about is why we might care about working at these long wavelengths in the mid-infrared, what's interesting about them, and why we might want to go nano at mid-IR wavelengths. So why do we want to look at things on the nanoscale with this long wavelength light? We've already actually had a couple of nice descriptions of the diffraction limit. I will do my best to basically go over that again, but maybe I'll sort of skip through that a little bit, since we've already discussed the diffraction limit twice today. And I'm going to talk about, well, I guess plasmonics and metal optics again, but I'm going to take a slightly different approach to this. I'm going to talk about what happens with plasmonic structures when we start going to long wavelength light. And you might be surprised it's very different, right? Metals look very different at IR frequencies than they do at the frequencies that Professor Liu is discussing. So I'm going to talk about what happens when we try to do plasmonics in the mid-infrared. I'm going to talk about these propagating surface plasmons. I'm going to talk about localized surface plasmons. I'm going to talk about how we might be able to use these structures for sensing, for making active devices, for controlling thermal emission. But I'm also going to talk about why these may not be the best approach towards doing plasmonics in the mid-infrared. And then I'm going to talk about something that Professor Liu sort of hinted about sort of a couple times, is the idea of designing materials for the optical response that you want. So in particular, I'm going to talk about how we can basically make our own metals to get the optical and plasmonic responses that we want at these long wavelengths. So I'm going to talk about how we make these metals, how we can integrate these metals into metamaterial or metasurface structures, and then I'm going to talk about how we can actually incorporate these with active photonic elements, all again looking at the sort of idea of how we can do sensing with these types of structures. Okay, so the first thing, first question I said I'd answer is why the mid-infrared? And so the sort of argument I usually make is that everything emits in the mid-IR. In fact, all of you are emitting in the mid-IR right now. You're not trying to, but by virtue of being at room temperature and not absolute zero, you are emitting thermal energy, and you're emitting that in the sort of wavelength range of between 3 and 30 microns, the mid-infrared. You're all probably around at 10 microns, and this is why if you take a thermal image of a biological object, for instance, a research group, my research group in particular, what you see is that they are all emitting thermal light. And the joke I always make is that they're thinking so hard that their heads are white hot in the thermal imaging camera, except for that person who doesn't seem to be thinking about anything. Okay, so everything emits in the IR, and of course what that means is that if you want to track something, say a person or a airplane, and I do not think we're actually allowed to thermally track or target graduate students, so we try to do that with airplanes and jets. That's a joke. We don't track graduate students at all, but right. So people are interested in looking at thermal signatures for these sorts of applications, but not so much for biological applications or medical applications. So out of curiosity, I just sort of typed in to Google thermography for sort of diagnostic applications, and a lot of came up. I mean, pages after pages after pages, but they all looked a little funny. They were all sort of like wellness clinics, and if you actually dig a little bit deeper, most of the sort of real insurance companies do not cover thermography because it is sort of clearly stated on numerous occasions that it is not a valid or a recognized diagnostic test. So people, I mean, if you actually look at most of the applications you're able to find on Google for thermography for diagnostic applications, as far as I could tell, people were making claims about breast cancer detection, so it just ended up being a lot of pictures, thermal images of breasts, basically, and I don't know that there are any real medical applications for that or medical value to that. So no real, as far as I can tell, not a lot of interest in sort of using thermal emission, but the fact that everything emits in the mid-IR also actually tells us, because thermal emission is very much linked to absorption. So if everything emits in the mid-infrared, it turns out that pretty much everything absorbs in the mid-infrared, right? And what that means is that everything absorbs, and not just sort of this broadband absorption, but different molecules have very, very distinct absorption patterns, right? And we call the mid-infrared in a lot of cases here referred to as the fingerprint region of the electromagnetic spectrum, okay? And that's because every molecule, or a lot of these molecules, have very distinct absorption spectra, right? So, and you can tell what molecule you have by looking at the absorption spectra. So what I'm showing here is the absorption spectra for ammonia, okay? So ammonia is not just a random molecule that I sort of came up with. People are interested in ammonia because it is a biomarker for kidney and liver function, okay? So the ammonia in your exhaled breath can actually tell you something about how your kidney or how your liver is functioning. If you look at the absorption spectra for ammonia, what you see is a series of sort of very distinct, discrete, narrow absorption resonances, and you see that these are strongest in basically the 8 to 12 micron range, okay? So what you have here is essentially a spectral fingerprint of a gas that people are very interested in being able to monitor in exhaled breath. And I'll talk a little bit more about exhaled breath in a second. But the same thing goes for, so you're not just looking at how the body is performing by looking at the emission from the body, but you can look at how, for instance, a factory is performing by looking at the emission from the factories. You can look at any sort of industrial process and look at what the output of that industrial process is, or the waste flow or the waste gas from that industrial process, and you can look at what molecules are present and at what concentration, and you can tell something about the efficiency of the process. In a sense, you can go one step bigger, and you can talk about the Earth as a factory, and you can look at sort of how the Earth's health by looking at the gases in the atmosphere, and of course, so for things like environmental monitoring, for looking at CO2 emission, all these sorts of things, right? We want to be able to detect the presence of these gases. We want to be able to do it quickly. We want to be able to do it non-invasively in a lot of cases. And so that leads us to looking and using these spectral fingerprints to be able to detect the presence and quantity of gases, right? So I gave the example of breath analysis, right? So the measurement of these volatile organic compounds in exhaled breath offers us the opportunity to detect disease early in the progression of the disease, okay? So this technique actually extends back to Hippocrates, and I guess, you know, even as far back as the Romans, they could tell that something was wrong with someone by actually smelling their breath, and I would imagine in the days before Crest and Colgate, that was probably not a fun job to have. But you also hear stories about dogs who can actually sniff. I don't know if those are apocryphal or those are true, but you know the very, you know, so the being able to sort of detect diseases by detecting the presence of sort of very, very small amounts of molecules in exhaled breath, or in trace amounts of molecules in gas, right? So there's a lot of interest in doing these sorts of breath analysis for, again, some sort of diagnostic and medical applications. And so if you look at what a breath analysis system might look like, of course it's fairly complicated, but it basically involves a laser that you're shining through these molecules that you want to sense, and essentially a detector, and essentially some sort of a grating, in this case, that gives you spectral some spectral differentiation, right? This is a slightly more complicated system than what, God forbid, you would blow in if you got pulled over by the police, although this guy actually looks like he might need one of those breath sensors as opposed to one for kidney or liver failure. So you can actually look at this sort of wide range. You can't probably, the resolution's not so good, but wide range of molecules that exist in exhaled breath, and they actually all are indicators of some biological function, right? And they all have sort of these strong, distinct wavelengths at which they present, right? And so you can actually get an idea of what is in exhaled breath if you can generate light in this spectral fingerprint range, right? And you can sort of scan. You can think about scanning a laser through this fingerprint range and looking at the presence of all of these different molecules and the relative intensity of these different absorption signals. All right, so there's a lot of sort of research being done, and again, like my previous two speakers, I'm trying to put references on every page so that if you're interested in looking at this more thoroughly, you can go through these references and sort of look at what's out there in the literature. Now, the one thing that you might notice here is what this compound down here. This is water. I'm not much of a chemist, but I actually know what water is. I also know that it is pretty much everywhere in biological systems, and they don't even bother, these are all parts per million, parts per billion. This is basically just percent. I mean, there's just, water everywhere, and it absorbs, if we look at the vibrational absorption, it absorbs everywhere, right? So right away we see that there might be some problems with trying to do some of the sort of microscopic or spectroscopic analysis in the mid-IR on biological objects, because unless you can get rid of the water, you're going to have real problems getting any light through anything at these frequency ranges, right? So this is why people are interested in things like exhaled breath and not doing sort of in vivo sort of mid-IR spectroscopy, because basically you absorb everything in the mid-IR, right? Okay. So if we think about the sort of advantages of using this wavelength range for bio applications, right? The advantages are multiple. So we get a direct measurement of molecular concentrations, right? So we can differentiate between different molecules because they have these different fingerprints, right? And we can get a stronger response, right, than, for instance, a third-order nonlinear effect like Raman, because this is a direct absorption as opposed to some sort of nonlinear effect, okay? Now, it's also not simply a measurement of index change, right? You're not just seeing a change in index. What you're seeing is a distinct, discrete absorption resonance, right? And so you're getting information not just about the sort of the macroscopic index of a material, but you're looking at sort of a direct response of a individual molecule to this light, okay? And it's all optical, right? So if you can do this, if you can actually do broadband sort of fingerprint detection, spectral fingerprint detection, then you don't require tagging, you don't require any sort of chemistry, any sort of labeling. It's, again, a direct measurement, right? But there are real challenges to operating in this wavelength range. First of all is that everything absorbs in the mid-infrared, right? So, especially water. So for instance, doing any sort of transmission measurement through a biological species is very, very difficult. Which means that you sort of have to go to dilute samples or gaseous samples, which means that you have a weak response. And the last thing is something I'm going to spend a little bit of time talking about, which is that it's very hard to work at mid-infrared wavelengths, okay? It turns out that these wavelengths are, yes, is there a question or no?
Yeah, but so basically, so it's saying a stronger response than let's say long spectroscopy. What is like the order of magnitude?
It's well, okay, so if you're not doing SIRS, if you're not doing sort of any enhancement of your Raman signal, I think it's on the order of 10 orders of magnitude in terms of the difference between the Raman signal and a direct absorption signal, right? So, and again, of course, it depends on concentration, but realistically, a trace gas, you can get a % absorption, but your Raman signal is much, 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 much smaller than that. Okay. So the idea is, with Raman, you can of course enhance it very, very strongly by using SIRS and other sort of techniques, but and and you can get orders of magnitude enhancement. People always talk about 10 to the 7th, 10 to the 8th. You're still looking at a sort of smaller signal than you would be if you're just doing a direct absorption measurement. Okay? But there are real problems working in this wavelength range, and I sort of want to give you an overview of the mid-infrared and what we use in the mid-infrared so you can sort of see what these challenges are. Okay? So the first, the sort of traditional spectrometer that we use in the mid-infrared is called a Fourier transform infrared spectrometer, or an FTIR. So this is what an FTIR looked like maybe 20 years ago. Basically, this is a Michelson interferometer, right? It looks at, you might use a source here. So this gives a broadband IR light. It goes through a beam splitter, and it's split into two arms. You have a moving mirror that changes the path difference between these two arms. It's recombined, and it ends up on the detector, right? And so what you can do is then if you look at the response of your detector as a function of position of one of these arms and then take the Fourier transform of that, what you end up with is a spectrum. All right? So you have, for instance, you could put a sample in that beam. Right? You look at the spectrum with the sample, you look at the spectrum without the sample, and you get the absorption signal of that sample in the beam. Okay? For the source, right, again, I'm talking sort of 10, 20, 30 years ago, what we typically use is a glow bar, which is basically just a resistor. You run current through it, it heats up, and it emits a lot of thermal energy, right? So this is basically nothing more than just a ceramic resistor that emits heat, right? We can have coherent sources. Again, 20, 30 years ago, the coherent source that you could use was a CO2 laser. This is a gas laser. It emits at certain discrete lines in between about 9 and 12 microns. But is not a continuously tunable. It is not sort of a pulsed laser system. It is not a small laser system. It is a tabletop system. And when I say tabletop, I mean the whole table. Okay? So again, if you want to make a handheld sensor to detect the presence of ammonia in someone's breath, but you have to lug around a CO2 laser, that's probably not going to work, right? Our detectors, for the most part, are sort of semiconductor-based detectors. In particular, the sort of detector of choice is what's called a mercury cadmium telluride detector. These are difficult to grow. They need to be liquid nitrogen cooled. We can have room temperature detectors. They tend to be much weaker and much, much, much slower. Okay? So this is sort of where the mid-IR was 20 years ago. And then something happened, actually, I guess 20 years ago this year. Federico Capasso's group at Bell Labs invented a device called the quantum cascade laser. I'm not going to go into a lot of details about the quantum cascade laser. This is a Biophotonics summer school, not a solid-state device summer school. As much as I'd love to spend the next hour on this, basically what you have is a very complicated semiconductor header structure, and you design it in such a way to make the electrons transition from an upper state to a lower state and emit mid-infrared light. And it works. Actually, it worked 20 years ago, and now it works much, much better. So, in 1994, all these devices were pulsed. You could only pulse them. You couldn't run a continuous current through them because they would heat up and blow up. But now we can operate things in continuous wave, which means there's a continuous current. We can operate them at room temperature, so you don't need liquid nitrogen cooling. We can get very, very high wall plug efficiency. Namely, if you put in a watt of power, you can actually get out half a watt of power, which is pretty good at these wavelengths. And these are semiconductor lasers, so they can be small, they can be compact, and because they're quantum engineered, you can design them to emit at pretty much any wavelength across the mid-infrared, right? So now we have room temperature, continuous wave, wavelength flexible, all the way from 3 out to 20 microns. These are broadly tunable devices. They are high power, so you can get these things to emit 5, I think now 10, 15 watts, and they can be high wall plug efficiency. Now, in fairness, most quantum cascade lasers are not all of these things at the same time. You can sort of pick and choose. It's always a balancing act, right? But you have a number of different groups in the US and in Europe working on these things. You can shape the beam coming out of the laser. You can make arrays of these structures where each one of these lasers emits at a different frequency. So you can essentially make almost like a spectrometer, right? A addressable spectrometer where you can sort of control the emission coming out of this very small compact semiconductor device. You can make them high power across a range of wavelengths. And you can do all sorts of novel resonators, high wall plug efficiency, and across a wide range of wavelengths, so all the way from sort of 3 microns out to 20 microns, right? And so these are exactly the sort of sources that you need if you want to do sort of chemical analysis of exhaled breath or sort of really anything. Having the ability to have a coherent source, a coherent semiconductor source, so now instead of lugging around your CO2 laser, you can actually start thinking about making handheld breath sensors, because your light source is coherent, narrowband, and about, you know, a millimeter in size, as opposed to being a tabletop, right? And of course, the most important thing is that you can buy these, right? So you can, well, you can't go to Best Buy and get them, and I don't think that Best Buy would want to sell mid-IR lasers, though that would be very convenient for me. But you can buy these. There's a number of companies that are actually doing very well selling quantum cascade lasers, and in fact, if you go to a sort of optics website, like a store like a place like Thor Labs sells quantum cascade lasers. This is a screen grab from the Thor Labs webpage, and you can go and buy a QCL if you have, at Thor Labs, if you have $5,000 on you. From Daylight, if you have about $30,000 or $40,000 on you, you can get one of these really nicely packaged external cavity quantum cascade lasers. So yeah, they're not cheap, right? They're still pretty expensive, but the price has been coming down, and you can get them commercially. So this is not just a sort of research lab type device. Mid-air detectors are something of another story. The state of the art is actually still the mercury cadmium telluride detector. It's a sort of wavelength flexible device, and you can use those for single element detectors, so just a single detector. You can make high-speed photovoltaics out of them, and you can arrange them into focal plane arrays, so you can effectively make like a CCD, but for thermal wavelengths. Those are really expensive, right? So you can buy a pretty cheap CCD or CMOS camera, right? You can buy those, about $100 you can get a pretty cheap one for now. This thing is going to cost you between $50,000 and $80,000, okay? So expensive, right? So very, very expensive. And most of these MCTs, in order to be very efficient, are liquid nitrogen or thermoelectric cooled, except for a lot of the photovoltaics, which are room temperature, but they don't respond very well to light. Okay? So there's been a lot of work and a lot of effort on developing next generation detectors for the mid-infrared. Now, a lot of this has been funded by the DoD, of course, because they are interested in tracking hot objects. But the beneficiaries of this research could be people in sort of sensing fields where you do want to have, you know, nice imaging arrays that are cheap, because if you think about all the wonderful sort of things you can do with an imaging array, and how much sort of cool microscopy you can do with those things, you know, if they're $80,000, it becomes really hard to sort of make handheld, compact, cheap sensor devices. So there's a lot of different people working on a lot of, so using quantum dots to do mid-infrared detection, using these complex type 2 heterostructures. Again, I'm putting up the references. I'm not going to go into the sort of physics. Making focal plane arrays, right? But still, the focal plane arrays work nicely at 120, but even by the time you get to 150K, so you're talking about, you know, minus 100, minus 150 degrees, they're really starting to fade already. Okay, so again, these are great at low temperatures, not so good. Okay, but we do have detectors. We do have now really, really nice lasers. And so let's think about what we actually need to have in order to make the sort of sensing systems that I was talking about earlier in this lecture, right? So what goes in here, right? What actually sits in there? You know, if we want to make a system where we shine light at our molecules and we look at the amount of light that is absorbed or transmitted, right, and we scan the wavelength of our laser back and forth to tell the, you know, the presence and quantity of a gas there. What do we need in here to be able to do that, assuming that we have this part, the laser, and that part, the detector, okay? So we've had this rapid development in mid-IR sources, right, and that's opened the door to all sorts of different applications, sensing, thermal imaging, tracking, but the source development has been a little bit slower. Or the source and detector development, has been faster than the development of what I like to call the sort of optical infrastructure. So all the things that you take for granted when you work with optics in the lab, the lens that you can buy at Thor Labs for $50, right? All those sorts of things, that doesn't exist as much in the mid-IR, right? So let's say you want to buy a polarizer. So you want to buy a polarizer because you work at visible wavelength range, right? So you can buy a polarizer for $80. I'm just going, this is off the Thor Labs website. And now let's say you want to buy a polarizer for the mid-IR. Well, you're going to pay $1,300 for it. And if you look at this thing wrong, the lines will sort of, I can't tell you how many grad students have cost me how many thousands of dollars by touching one of these polarizers the wrong way or breathing on it and then it's shot. So not only is it incredibly expensive, but I mean, Scott, you know, right? These things go very quickly. Okay, so that's about at least an order of magnitude, maybe a little bit more. Okay, let's say you want to buy a really nice lens. Really nice lens, right? You can get one of those, you know, for the telecom wavelength range, $110 in the mid-IR, $800. Again, about an order of magnitude difference. And by the way, you're lucky that you can even get this because 10 years ago, you wouldn't be able to find that even on the Thor Labs website. You couldn't buy it. Let's say you want to buy an electro-optic modulator for telecom wavelengths. Okay, that's great, about 2K. That's not cheap, but that's not bad. In the mid-IR, no, forget about it. It doesn't exist, okay? So all of this sort of, the stuff that you guys probably take for granted if you work in the IR or the visible are things that I would love to have and that I would pay dearly for and that I, in fact, in many cases do pay dearly for. Okay, so what we want is we want a mid-IR infrastructure that allows us to basically interact, to have the molecules that we want to sense interact with this long wavelength light, okay? So here's our molecule, just a random molecule I put up there. The molecules are pretty small, okay? And let's look at our mid-IR light. I just put a very simple sine wave up here, right? And so let's compare the size of our mid-IR wavelength to our molecule. That's not going to work. So let's, okay, that's still not right. I'm getting there. That's probably about where we are, right? So when people talk about going nano or sort of doing nanophotonics at visible wavelengths or at sort of near IR wavelengths, that's great because you're going from sort of wavelength of 400 nanometers. I mean, your wavelength in the visible is you're already nano. You don't have to do much, right? You're already doing nanophotonics because the wavelength of your light, you know, between 400 and 700 nanometers. At 9 microns, trying to figure out a way to get your light into a sort of nanoscale volume, now that's really challenging. That gets tough, right? And if you want to interact with a molecule, if you want to enhance that interaction, well, you got to work really hard to get this down to that scale, okay? So the small size of our molecules that we want to sense means that a simple single-pass system, right, if you're trying to do trace gas detection, just shining a laser through a cell with parts per million, parts per billion molecules that you want to sense, that's probably not going to work, right? Okay. So you need to somehow enhance that interaction. And there's a couple ways that you can enhance the interaction. One is don't pass it through once. Pass it through a bunch of times. So you can make multi-pass cells, right? You can make a cell that has an effective length of, you know, tens of meters or kilometers if you design it well, as opposed to sort of this just single pass, you know, tens of centimeters, okay? You can do a cavity ring down technique. Professor McCall's research group here at University of Illinois does cavity ring down spectroscopy. Basically what you're doing in all of these cases is you're giving your light a lot of opportunities to interact with the molecule. You're not necessarily changing the size of your mode. You're just making that mode interact many, many times. And even if the probability is weak for any given pass, you make the light go back and forth 1,000 times. All of a sudden, you're improving the chance of an absorption event happening. But the other approach is sort of something that Professor Liu was talking about in the previous discussion, which is maybe there's a way to enhance, and actually Scott was talking about this as well, maybe we can use plasmonics to enhance light matter interaction. So instead of sort of just brute strength making the light go back and forth and interact many, many times with the molecule, let's just try and condense our light down into a nanoscale volume. Let's try and get our micron scale light into volumes comparable with the nanoscale, right? Well, it turns out that this is easier said than done, and it's easier said than done because of the diffraction limit. Turns out light does not like to be squeezed into volumes smaller than its wavelength, or much smaller than its wavelength. So we see this all the time when we try to, for instance, make a dielectric waveguide, and we try to make the waveguide smaller than the wavelength of light, or much smaller than the wavelength of light. The light doesn't want to do that. And what it basically does is just expands, and you get this sort of very poorly guided mode. It's still guided, but it's very poorly guided, right? So you can't just take a dielectric waveguide and shrink a dielectric waveguide and assume that the light is going to stay in that shrunken waveguide. We see the diffraction limit when we try to image two objects that are very close together, and as was discussed by Scott, we see the diffraction limit when we try to focus light. So you might say, okay, you have long wavelength light, who cares? Just focus it down to a spot and you'll be fine. Well, it turns out that, as Scott discussed, you can't do that. You can't focus your light down to a spot smaller than, you can't go smaller than lambda over 2, much smaller than the wavelength of light. So you're always going to get this sort of this airy disk when you try to focus your light to small volumes. And of course, when you have mid-IR frequency light, you're talking about wavelengths on the order of microns. So you're not going to be able to get your light into a nanoscale volume because of this pesky diffraction limit. So how can we beat the diffraction limit? Well, we can try going to shorter wavelengths, and then that sort of just means that everything I've been talking about for the last half an hour was a waste of your time, right? Because I made this argument that we want to work at this frequency range because it contains all of this valuable information. Okay, so let's not do that. Let's not give up on the mid-IR yet. Well, we can go to sort of higher index materials, right? We can basically try to image through immersion devices, or we can do solid immersion lenses, and that's good, right? We can gain basically a factor of an index of refraction for index material, but in the mid-IR, we don't just need to beat the diffraction limit, we need to clobber it, right? So, a factor of 3, or a factor of 1.5, it ain't going to do it. We need sort of orders of magnitude in terms of beating the diffraction limit, right? So what about plasmonics? So we've already seen what plasmonic materials can do for nanosensing at short wavelengths, right? Professor Liu had a really nice discussion of this, and Scott touched on this as well. So we know what plasmonics can do in the visible and near IR, but let's see what plasmonics can do at longer wavelengths. Okay, so I'm not going to spend too much time here. The one thing I want to remind you, and this was brought up in previous seminars, was basically that the optical response of a metal comes from the behavior of electrons in that metal, and in particular the behavior of free electrons in the metal. So it is the sloshing around of those electrons that gives us this permittivity of the metal, right? And we can describe this with the Drude model that Professor Liu alluded to before, basically assuming that you have free electrons, and I will add one more thing to that model, and that is a scattering time or a damping time. This damping time effectively corresponds to losses in your metal, and these losses are actually pretty important. So we have to take these into account, right? So if you include the scattering, what you get is an expression for the permittivity of your metal that looks very similar to what we saw in the previous lecture, but we have this imaginary component, this complex component to your permittivity that effectively describes the losses in your metal. And again, we have this plasma frequency, which determines essentially the frequency at which your material goes from being a lossy dielectric, so it allows light to propagate, to being a metal, where it effectively reflects your light. Okay? So the permittivity of your metal is basically results from the response of free, and also you have this sort of background response of the bound carriers to an electric field. Okay, so then if we look at the interface of one of these metals with the interface of a metal and a dielectric, what you get are these bound propagating surface plasmons, which you've already seen a couple times already today, and you get this dispersion relation, which you've already seen. And the only thing to recognize is that this surface plasmon polariton, this bound surface wave, propagates on a metal surface and is tied to the metal dielectric interface. We can also have these localized resonances, and again, we're making the quasi-static approximation that Professor Howard talked about earlier, right, where basically you're assuming that the light, the wavelength of your light is much, much larger than the size of the nanoparticle that you're dealing with. And this localized surface plasmon is not surprisingly, is localized. It's tied to a sub-wavelength particle in 3 dimensions. Okay, so I'm not going to go over this too much more, but I do want to talk a little bit about sort of where we're seeing plasmonics. We're seeing plasmonics as waveguiding for sub-wavelength lasers, so for nanoscale lasers. People are interested in plasmonics for guiding light, for instance, on-chip optical interconnects. You've already seen this picture today, so for filtering. Of course, the plasmonics is basically the localized surface resonance is behind the sort of SIRS effect. This was mentioned by, I believe, Scott, you talked about this idea of sort of photothermal cancer therapy. And even more recently, the Hollis group at Rice has shown that they can boil water using localized heating from these nanoparticles without changing the bulk temperature of the water. So they can keep water at 32 degrees Fahrenheit, and they can locally boil water by heating up area very, very near these nanoparticles and then actually vaporizing the water and essentially creating water vapor in water at basically room temperature or even colder. Okay. So why do we care about plasmonics? Well, I hope we've already gone over this a couple times. So for the sort of the propagating waves, for optical interconnects, for enhanced sensing of maybe thin films, right, and for strong interaction with sort of surface geometries. In the 3D case, for the localized surface plasmon, we care about enhanced interaction with sub-wavelength molecules, detectors, or light emitters for solid-state applications, enhancing nonlinear effects, right, or for localizing the absorption or heating for photothermal applications like photothermal cancer therapy, right? But if you look at most of the work on the above slides, and actually most of the work in that exponential curve that Professor Liu showed, what you see is that all or most of that work is done at short wavelengths. And the question is why, right? Well, let me show you what the difference is between operating at short wavelengths and operating at long wavelengths. So this is not related to bio. This is a beam steering plasmonic structure. It's not so important how it works, but basically light comes in through this sub-wavelength slit. It couples into these propagating modes. It scatters off these little corrugations, right? And that light scatters into the far field. It interferes, and it gives you this beaming effect as a function of wavelength. So we made the same thing in the mid-IR. So you might say, okay, well, there you have a propagating surface mode. It looks exactly the same in the mid-IR as it does in the near-IR. Let's do some sensing with localized surface plasmon resonances, right? So if we look at the sort of typical approach to doing these sort of sensing experiments with LSP structures in the visible or the near-IR, right, you look at an index change that comes from putting something on top of your localized surface plasmon resonator, and you see that change in the reflection or the extinction spectrum from your particle array. And so you can do that same thing in the mid-infrared, right? You can have an array of these localized resonators, and you, for instance, can put silk on top of that in this case, and you see a change in the spectral response of those resonators. But if you look really carefully on these structures, and this is some work from my group, what you notice is the scale of these structures. They're still micron scale, right? And in fact, if you actually look closely, they're effectively wavelength scale, okay? And what that means is that you can't go nano for these localized resonators. So let's think about why. Well, it turns out that scaling from your sort of visible response to your mid-IR response is not just a matter of scaling size. You have to think about permittivity. And if we look at the permittivity of a metal in the visible and near-IR wavelength range, it's negative, but it is, on the order of -10, -2, in that range. As you go out to the mid-IR, you're talking about permittivities, the real part of your permittivity is the order of negative hundreds, negative thousands. So that's actually, it's a really good metal, but it's not a really good plasmonic material. Because if you look at the dispersion relation for a propagating surface plasmon, in the visible, right, this curve, when it curves over and you get these sort of high K values, right, that's when the wavelength of your light gets really small. That's when your confinement gets really small. That's when you get really plasmonic, right? But when you're operating down here, you can't really tell the difference. This line, this red line, sits right on top of the black line. That's the red line's the behavior of just a light wave. The black line's the behavior of your surface plasmon. And you can't tell the difference, right? It's basically the same thing. So there's no real difference between a plasmonic wave and a light wave at the mid-IR when you're operating with these traditional metals. All right, so you can look at, in this case, the penetration depth, right? If you want a sub-wavelength mode, you want to confine that light to very, very small volumes. Well, you can do that in the visible near IR, and this is normalized to wavelength. So if you look at in the sort of mid-IR wavelength range, your mode extends 10 wavelengths above the metal surface. Not only is that not sub-wavelength confinement, that is not, I mean, not only is that not sort of nanoscale confinement, it's not sub-wavelength confinement. You're talking about 100 microns of penetration depth. That is not a particularly good enhancement of your electric field. In fact, you could argue it's quite the opposite. Now, the advantage is that these things propagate for very long distances, right? So you can propagate the surface plasmon for millimeters, but that's because it's not really attached to the metal. So you're propagating a mode in free space. Now, you can do all sorts of fun things with these modes that propagate for long distances because, you can, for instance, create these weird arrays of gratings that are not periodic, but that can actually focus scattered light above the surface. But ultimately, if what you're looking for is sub-wavelength confinement, you ain't getting it with the propagating surface plasmons at these long wavelengths. Well, what about the localized surface plasmon? Well, why don't you, forget about these propagating modes, just localize it to a nanoparticle, like Professor Liu does at visible frequencies. Well, if you look at the response, right, the polarizability of a nanoparticle, it's given, the resonance is given by this denominator. When this denominator goes to 0, you get a very strong optical response. Well, this denominator only goes to 0 when the sort of magnitude of your metallic permittivity is on the same order as the surrounding dielectric permittivity, right, but negative, right? That's what sends this term to 0. But we already know that the metal permittivity in the mid-IR is minus 1,000. So unless you have a dielectric that has a permittivity on the order of positive thousands, which you don't, but if you do, get in touch, we can talk, right? You're not getting that localized surface plasmon resonance. So it can't happen. You can't even get that. You can't even confine your mode on a traditional metallic structure to a localized surface plasmon resonance. Okay, so if we look at sort of where we are right now, right, so the traditional metals allow for sub-wavelength confinement at short wavelengths. So you can get enhanced sensing, you can do nano-optoelectronics, you can do nanophotonic waveguiding. And you have lots of losses, but fine. Okay, you can do all these sort of nano sub-wavelength type things. At long wavelengths, we can use antenna-like structures. These are antennas. These are not localized surface plasmon resonators. Despite what people say to try to get published in Nature Photonics, these are not localized surface plasmons. These are antennas, okay? Because your metals are behaving like perfect electrical conductors, right? And so that's equivalent to basically building something that's scaled down from the microwave frequencies or RF frequencies. So we can't go to wavelength, or we can't really even go to nano, right? Unless we make our own metals, right? The problem with, the reason why we can't go nano is because we're stuck with gold and silver. That's what everyone uses for plasmonics. But what if we don't use gold or silver? What if we just make our own metals? What if we make metals that we control the optical properties? So this is why I put up that slide at the beginning of the talk, because if you remember, I said the optical response of a metal comes from the behavior of the free carriers. So what we need is a material where we can control the free carriers. If we can control the free carriers, then we can make our own metal. Well, it turns out that people have been doing this for years with materials that we like to call semiconductors. Semiconductors are materials where we can control the electron or hole populations. We typically use those for electronic devices to control the conductivity of a semiconductor. But that's what makes semiconductors so important. That's why your computers run on semiconductors, because you can control the conductivity of a semiconductor. But that conductivity comes from free electrons. And so if you can control the number of free electrons, you can actually control the optical properties of a semiconductor. So this is the permittivity of a semiconductor again, this is the Drude model. And if we go back and we look at that plasma frequency that Professor Liu was talking about, we see that it depends on the free carrier concentration and the effective mass. So if we have a small effective mass and a large free carrier concentration, we can actually push this plasma frequency for a semiconductor, not a metal, but a semiconductor, into the mid-infrared, and we can basically make our own metals. So let's look at what one of those metals might look like. So what I'm looking at here in black is the reflection from a doped semiconductor structure. This is an indium arsenide semiconductor that we basically just, as I like to say, we've doped the snot out of it, okay? So what happens as we go to longer wavelengths? So as we go to longer wavelengths, the material goes from being a lossy dielectric to a metal. And what happens to the reflection is you get these oscillations. This is just the Fabry-Perot oscillations in your doped indium arsenide layer, which here looks like a lossy dielectric, and here looks like a metal because you can see that the reflection is essentially going to 1, right? And we can model this with a simple Drude model, and we can extract from that our epsilon. So we can actually design a metal where we control the permittivity. We decide when it becomes a metal. We decide where the plasma frequency is, and actually we can, to a certain extent, control the losses. And the losses, remember this imaginary part of your permittivity, they actually look much better than gold. If you look at the losses of gold at the visible and the losses of our metals at the mid-IR, our metals are better. And that's actually kind of cheating, because the reason that gold is gold is because it has a lot of interband absorption. Right? So that's why it actually is gold. Those absorption resonances give you losses near the plasma frequency. Okay. One other kind of cool thing is that when you, and the technical term, remember, is doping the snot out of a semiconductor, when you do that, what you actually do is you make your semiconductor transparent out to near IR frequencies. This has to do with the filling of bands in the semiconductor, but ultimately these semiconductors, while they are usually would absorb light at telecom frequencies, these are actually now transparent out to telecom. Okay, so I want to talk a couple of, just to give you a couple examples of kind of cool things that you can do with these designer metals. So the first is, Professor Liu talked about this concept of the plasma frequency. Now, the plasma frequency is where your metal goes from being a metal to a dielectric. But at the plasma frequency, the permittivity of your metal is 0. What does it mean to have a 0 permittivity material? Well, if you think about what that means, what that essentially means is that your index of refraction becomes very, very small, negligible. And so the wavelength of your light in that material becomes extremely large. So if you think about a wave propagating through an epsilon near 0 material or an E and Z material, instead of sort of seeing those wave fronts that typically propagate along the material, what you see is the entire material is basically oscillating with the same phase. Every point in space in that material is oscillating back and forth with the same phase, okay? So there's a couple of things that we're interested in here. One is that it turns out that that type of excitation couples very nicely to ultra sub-wavelength waveguides. So we basically just put a very small slit on top of this E and Z material, and we see this very strong peak at the E and Z frequency where we're essentially funneling energy into a sub-wavelength peak. The other thing that's kind of cool about this is if you think about a sort of traditional circuit. In a traditional circuit you have resistors and capacitors and inductors, and you rarely think about the wavelength of light for a lumped circuit element, right? But if you actually thought about the frequency that these things operate at, the wavelength would be much, much larger than your resistor, your inductor, or your capacitor. We don't really have the equivalent in optics. But if we can design a material that sends the wavelength of our light essentially to infinity but keeps the frequency the same, then we can start thinking about making optical circuits using these sort of lumped elements that we think about for sort of what you learn about in your first semester electrical engineering class. Those layered metamaterials that Professor Liu was talking about, well, we can do those. We can do those in our epitaxial growth system, and we can do them without having to change materials or anything. All we do is we open or close our doping shutter. So we can grow these layered metamaterials quite easily and again, we can control the metal properties, something that you can't do at shorter wavelengths. And so we can grow layered structures that give sort of designed absorption resonances, right? And we can control where the modes are in these sort of ultra-thin, undoped structures. So we can sort of funnel light into sub-wavelength modes, and we can put that light either outside, so we might be able to use that for sort of sensing applications. We're concentrating our light outside of our sort of doped semiconductor, or we can couple it into an undoped region, and we can sort of enhance interaction with maybe an optoelectronic device in that structure. Okay. Now, I showed you a slide earlier where I said, well, there's no difference if you look at sort of the beam steering effect. There's no difference between the mid-IR and the visible. That was true in terms of the macroscopic response. That's not true in terms of what was going on the surface. In fact, as we know, if we look at the surface, your mid-IR mode is extending way, way out. Your near-IR mode is very tightly confined, but you can't tell from a distance. So we claim we have all these really neat properties, and a mid-IR metal like this should be able to support a localized surface plasmon. But let's see if that's in fact the case. So we can basically pattern our semiconductor into these little localized resonators, and we can see some sort of extinction response from that. But again, just because you see something in the far field doesn't mean that it's the same behavior in two different systems. So what we did is we looked at a system where we were actually able to excite one of these little localized resonators. So we hit it with a laser, and we looked at it as it absorbed that light. So we looked at this absorption resonance, and as it absorbs light, it actually heats up and it expands. Right? So this is basically an infrared atomic force microscopy, because we have a cantilever probe that as this thing expands, it pushes up the cantilever probe and delivers an impulse to the cantilever. And you can actually measure the deflection of the cantilever and see how much things are heating up as a function of the wavelength of your light and as the position of the cantilever itself. And so if we look at our microparticles, you can actually see this localized heating in the microparticles. So not only do you see that, yes, we are locally absorbing light, you can actually see where on the nanoparticles or the microparticles you're absorbing light. This is light that's polarized like this. You're sloshing electrons back and forth. So it's not surprising that you're getting the most heating on those sides of the particles. We can change the frequency of our excitation pulse, so we know where spectrally our absorption resonance is. But those are microparticles. Let's see if we can go to the nanoscale, because ultimately the title of my talk is how can we get micron-scale light to nanoscale wavelengths. So this is sort of our recent demonstration of that, where we've actually gone down, we've taken 10, 11, 12 micron light, and we've been able to sort of get it to interact resonantly with nanoscale structures. And the way we do this is very similar to the nanoscale localized surface plasmon resonators that you've seen in the previous two talks. But we wouldn't be able to do that with metals, with traditional metals. We need our designer metals to be able to do this. We need to be able to control the optical properties of our metals, else we could never get to these sub-wavelength scales. So we grow our doped semiconductor material about 200 nanometers thick, and we put that on top of an undoped layer, and we etch down using this nanosphere lithography technique, where we basically spin on these nanospheres and they use them as an etch mask. Right? And so what we end up creating is a sort of an array of these nanoscale resonators. Right? So these should have an optical response, a resonant optical response, a resonant interaction with long wavelength light that depends only on the permittivity of the material and not on the geometry of our structure, to first order at least. And in fact, that's exactly what you see. If you look, these are modeled and experimental results. What you see is a sort of strong antenna-like reflection signal that comes from the doped material. If you look at the undoped, we did the same thing with a control sample and undoped material. What you see is there's absolutely no response from the other. So this is purely coming from the patterned doped material, and we can tune the response by simply changing the number of free carriers in our material. And what this means is that we essentially have a localized resonator structure, right, where we're coupling this long wavelength light to a nano resonator that's about, lambda over 20, lambda over 30 in size, right? And we can we cover this with very, very thin layers of PMMA, about 500 nanometers, so much, 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 much smaller than the wavelength of light, right? What we see are these sort of enhanced responses when the absorption resonances of our PMMA line up with the resonance of our antenna structure, okay? Now, the last thing I want to talk about before I end today is the idea of, one of the really cool things about being able to make these plasmonic structures on semiconductors is that we can think about integrating our metals, our plasmonic or metamaterial structures, with optoelectronic devices. We know we can make optoelectronic devices out of metals, right? Out of semiconductors, excuse me. So maybe we can make some sort of emitter, and we can have our source and our plasmonic structure, and maybe if we're really smart, we could even put a detector all on chip, all out of the same material, right? And do sort of mid-IR sensing, mid-IR spectroscopy on a single chip, right? Using metamaterial structures and enhanced concentration of light. So the structures we're looking at are actually, I'm not going to go into the details of the quantum dot growth, but these are basically indium antimonide dots, and they're grown on the same material system that we can turn into metals, as I've shown in the last few slides, right? And so what you can see is that we can, these are very nice, these are basically LED structures made out of these quantum dots, and you can see that we can get coverage from 4, in this case out to about 5.5, 6, but more recently we've shown that we can actually get out to 7.5, so we can cover most of the mid-IR in, again, the same material system that we make our metals out of. So we have now this opening where we can not just only think about making these passive structures where we have, you know, a mid-IR metal. It's a very expensive way to make metal, to grow it by molecular beam epitaxy. But if we can integrate that with an optoelectronic device, an emitter, a detector, or both, now we can sort of start thinking about these monolithic optoelectronic / plasmonic metamaterial structures where we can actually design on chip all of the sort of functionality that we're interested in. Okay, so I started off by talking about mid-IR plasmonics, or mid-IR optics and photonics in general. I talked about how we can do mid-IR plasmonics with traditional metals, but I also talked about how that is difficult and what the sort of challenge are associated with that. Namely, it's very difficult to get this enhanced light-matter interaction when your light extends over many hundreds of microns, right? So then I talked about how we can actually make our own metals, right? We have these crystalline, low loss, you know, single crystal, low loss, high quality, wavelength flexible materials. They can support localized resonance. We can get precise atomic level control over these materials. We can use them for IR sensing applications, and we can integrate them with potentially 3-5 optoelectronics. We now have light emitting structures, light detecting structures that are directly integrable with these sorts of plasmonic materials. This is of any interest to you. We actually did a review paper last year in Nano-Photonics that sort of talks a little bit about why we're moving towards, or how we're moving towards doing this sort of nanoscale photonics with micron-scale light. So with that, I will end, and if you have any questions, I'd be happy to answer them. Thank you so much for your time. Yeah, that's a question. So the short answer is yes. I mean, you can gate a semiconductor. But the sort of long answer is that when you're this highly doped, it's very difficult to gate more than, you know, a few nanometers, tens of nanometers. And then you start to basically, you get all sorts of tunneling problems and these sorts of things. So in terms of making it tunable, that's very difficult to do by controlling carrier concentration. It's something that we had spent a couple years playing around with before we sort of decided that that wasn't going to work. That wasn't going to work. Yeah.
Yes. I was a little confused about what you're using in your field interface. Was that just a comparison?
So that's a good question. The question is, why were we using the near field AAM? So the argument I make is that, you know, in a lot of these sort of plasmonic effects, it's impossible to know what's going on in the near field. So for a propagating surface plasmon, if you look at the optical response of that of a structure that can support one of those modes in the mid-IR, it looks exactly like what you'd expect in the visible and near IR. What you can't see is that that mode extends for hundreds of microns. So you don't know how poorly confined it is. It looks, in the far field, it looks exactly the same. You say, oh, I have some angle in which I couple, isn't this great? So it's only when you really get down to the sort of near field that you can actually tell, hey, look, what I'm doing is I'm sort of concentrating my light. I have these localized resonators. So the reason why we went to the IR AFM is because we wanted to get a nanoscale picture of where our structures were absorbing light. Okay, and so what the IR AFM does is it allows us to essentially determine the thermal expansion of our structures as a function of frequency and as a function of position. And for the position, we actually have about 100 nanometer or less resolution in terms of sort of the localized heating. So we can actually map out the localized absorption of a surface at these sort of long wavelengths, essentially. So it's an indirect measurement, but in some ways it's
it at least allows us to paint a picture of what the mode looks like for these localized resonators. So that's why we used it. Because otherwise, you can image something on that length scale using visible light, but you can't get the IR response on that length scale because of the diffraction limit. Right?